Ready? Hello, I am Michelle Davis of the Center for Manufacturing Research at Tennessee Tech University in Cookeville, Tennessee. Welcome to the Spring 2019 Golden Eagle Additively Innovative Virtual Lecture Series. This is the 7th semester we have produced this popular and informative series. This series is hosted by TTU's Center for Manufacturing Research and the iMakerspace at TTU. The CMR is recognized as an accomplished center of excellence that draws together resources from the state of Tennessee, the university, industries, and government funding agencies into a cooperative effort to be on the leading edge of the latest technological advances in the manufacturing field. The iMakerspace, located in the Volpe Library on Tennessee Tech's campus, has a goal of providing an interactive and collaborative space for students and faculty to use in pursuit of innovative and entrepreneurial projects. Additive manufacturing is a focus of both entities, and as such, this short virtual lecture series has been planned to highlight the best practices, potential problems, technological advances, innovations, and scientific contributions in additive manufacturing, with expert talks from various institutions, industries, R&D centers, and laboratories. Today, we are honored to hear from Eric Wooldridge, Professor of Additive Manufacturing at Somerset Community College in Kentucky. His talk is titled, "The Phantom Hole Technique, Improving Structural Performance in FFF, FDM, 3D Printed Products." We request that you mute your microphones and phones during this presentation for the most optimal experience. The speaker will provide his contact information for questions after the presentation is over. Thank you, and I turn the presentation over to Eric.
Well, thank you, and good morning. Again, my name is Eric Wooldridge, and good afternoon, too, in some cases. My name is Eric Wooldridge. I'm professor of additive manufacturing at Somerset Community College, and also the director of the Additive Manufacturing Center of Excellence here at SCC for our state KCCS system. And as mentioned, our title is The Phantom Hole Technique. Let me share the screen, and we will get started. All right, so what we're after with this technology is the application of improving performance with FDM, FFF, your typical low-cost additive manufacturing equipment. And it is an honor to be able to share this material with you. We definitely thank Tennessee Tech University, AM Watch, and all those involved for the opportunity, because this has been a big passion of ours. And so we start off the process with the acknowledgement that most everyone out there probably understands desktop 3D printing, additive manufacturing. You start off by creating a model in a CAD file. You take that CAD file, you put it into a slicing program, which writes the code, and the code tells the machine what to do. And this is a typical simulation of what you might see an additive manufactured part look like going through this process. So we see things like the external perimeter walls, we see the internal infill, and we see, of course, the outside shape. And most who are used to this process, and this, by the way, is Simplify 3D's screen capture. We use Simplify 3D a lot in our lab for production. But most are familiar with the process. When you're looking at these options for internal structure, you're fairly limited. You can make changes to the number of internal wall shells, you can change your infill, you can change your type, and you can make settings inside. So for example, we can take our infill percentage from 10% to 30%. We might be able to change it from a honeycomb design down to a rectilinear design. We might even be able to add a solid diaphragm throughout the entire part. We can also increase our shell count, but that's about the extent of your options with a typical slicing system. But in reality, that may not be necessary. In reality, let's think of a beam and place that, let's say you take a piece of wood and you lay it across a canyon and you walk out on it and you start jumping up and down. What's going to happen is you're going to stress the beam in the center, and you're going to stress it at the top flange and the bottom flange. So if that beam breaks, your solution for additive would be to turn around and go back to your slicer and add in more infill. You might increase it from 15%, 20%, 30%, and get it denser and denser until it doesn't break anymore. And that actually would solve the problem. The problem you're also creating, though, is now you have material where you don't need it. So you might have increased the material here, but you've also, by default, increased the material here and here where there was no stress on the beam to begin with. So the problem, the issues are you're creating material where you don't need it. You have no real control of internal customization for internal structural response. And not only that, you're just increasing production time. When you actually take longer to produce more material or to fill in spaces you don't need, you're increasing your production time overall. And of course, the question comes up, well, why do we care? Why is it necessary? Why are we even thinking along these lines? Why would we be too concerned about using low-cost additive to produce parts that are structurally more sound? Well, for one thing, here at the AMCOE, yes, we do have more advanced equipment, but we also have a very strong passion for low-cost additive manufacturing because it's a great startup for some small businesses. And also, there's some companies around the world that are doing great work with this type of technology. Many of us may already be familiar with Prusa Research and what they're doing. Their printers are worldwide, they're award-winning, they're low-cost. And if actually you look at those printers coming out from Joseph Prusa Research, you'll notice that about 20 parts are 3D printed by its brothers and sisters, using low-cost 3D printing technology to actually print parts for end-use consumer products. And they're not the only one. You look at what Lulzbot's doing it, they're doing as well. You've got folks out at Vision Minor where they're using this type of equipment for a little bit higher end material and FDM production. You look at MC Digital Armored, where they're actually using low FDM equipment, desktop equipment, to produce weapons accessories and lawn and garden parts. Even our military forces are using this type of technology to produce end-use goods. So there is a need and there is an application for better fabrication time, stronger parts, better performance. And so it'd be great if we were able to tell our slicer programs like Simplify and say, well, you know what, I need a solid zone of material right here. Or I need a solid zone of material right here. And the rest of it can be open infill. We don't have to get super high concentrated. But we don't really have that option, at least in the typical slicing programs. So with that, we'd like to introduce what we refer to as the phantom hole solution. It's a little piece of technology we developed about a year ago, last spring. We've been testing it out. It works really, really well. And hopefully today you'll find it very useful for your own production work. So the phantom hole technique is based on this. You're going to design optimized zones of concentrated material in your CAD model by making impossible holes. So essentially what you're going to be able to do with this technique is you're going to be able to go from this in your typical slicing methodology, your infill, concentrated, and honeycomb, to this, where you're able to put solid concentrations of material in any shape that you want it to be and reduce your infill where you don't. So it's going to take you from the way we have been doing it to the new way where it's optimized internally. Well, here's how it works. What you do is you go ahead in your CAD package. In our case, we're using Fusion and Inventor. Some folks might be using SolidWorks, CATIA, Pro-E, Onshape. And you go ahead and you design the outside of your part as normal. But then you go inside the part. You go inside the part and you design a hole that's so small that the printer can't actually make it. That's why we call it phantom hole. It's there, but it's not really. Your slicer will take that file and it'll look at it and it will see that there's a hole there, but instead of actually making the hole, it'll code it for it, but it will also add the external perimeter wall around the hole, as you see here. It'll think it can make it, but the printer can't do that kind of small size, and so what happens is the internal walls that it makes around it fuse together and merge. And so you get a structural shape based on a hole that's not there. So I'll do a quick demo for you to kind of see how the process works. I have a couple of parts created here in Autodesk Inventor. And you can see this is a 10 by 10 rectangle, about 35 millimeters long. And I have designed in a rectangle starting from the center. That is about 0.09 wide, 5 millimeters tall, and sort of floating about 0.8 inside the hole. It's extruded about 33 millimeters, so it doesn't come out to the end. And it's a cut, not an extruded shape. So we've actually cut a hole in this part, although from the outside, you can't see it. Here's another model where we have a pattern of phantom holes about the same size, one perpendicular to the others, to reinforce this wall and create a stiffener. And then we have a control part, 10 by 10 by 35, no phantom hole. We load those up into our Simplify 3D. They look the same on the outside. But when you run the slicer simulation, you find out it's actually created internal structures around the infill. If you want to see it more clearly, we can go back and adjust our infill settings, drop those down just a wee bit more, and you can see what it's done. You've got solid structure right inside, matching the shape of your phantom hole design, but there's not actual holes, and no infill, you don't need it. So here's the control, there's the optimize, and there's another one. So that's how the process works. One moment. And obviously, with any kind of new technique, we need to do some testing and kind of see the realities of it, limitations of it. So we designed 3 case studies. The first case study was essentially what you've just seen here. We actually just designed in a phantom hole into a part, ran it through the slicer simulation, compared to the others. Case study 2 was actually some fabrication with more complex shapes. And case study 3 was actually making the shape specific for certain types of forces and see how they perform out. So case study 1, basically what I've shown you already. You're seeing the actual part inside the cross section of the block, about the same size. And it's extruded 33 so it doesn't penetrate out. It's also mated up with the control part. And as we saw in case study 1, it was able to fabricate. What was really interesting, of course, is the fact that you could go back and make setting changes. You could go back and change your infill, reduce it down, increase it. You could actually change the number of your internal perimeter walls, and the phantom holes still showed up. So your slicer gets to operate as normal with no real interference, while at the same time creating this custom internalized structure unique. So in this case of this particular part, it might look the same on the outside, but this particular wall is now reinforced by this stiffener being in place. So with case study 1, we realized you're essentially going to be tricking the slicer into making the internal structure that you want, because it's going to see it as a whole. It thinks it can make it, the printer actually can't, and the internal walls that it makes around it are going to fuse together and be that shape for you. So it also allows the slicers to handle things as normal. So your infills and those kind of things don't have to be manually adjusted for specific things. You change those at will. Case study 2, let's try more complex shapes. So in this case, we tried the same shape that we were doing. We also tried some complex curves that were even unconstrained. We did rings of phantom holes to create internal cores. We also experimented with what our limits were in terms of overall size. At what point do we cross the line when suddenly our printer can actually make the hole? And you can see different variations of the designs we did. This one was our control, and this one was a nice, cool little spline feature that we actually used to reinforce both this side and this side of the actual walls of the part. And we used an unconstrained curve here to make this happen. Tested them out. There you see the results. We were able to fabricate them just normal. It was actually straightforward. They printed off just as they simulated. And you can see the cases where we created the solid core here, solid cores here, made our hole just a little bit too big, and so we ended up actually having a hole in place. Our splines with the 3 there were a little bit too large, so they actually ended up having holes. But there's our original one from case study 1, and more of the same. This one especially has the reinforced walls, and you can see it's a solid because we actually made the phantom hole small enough where the printer couldn't actually fabricate it. And you can turn around and take the infill out altogether. So this one has 0 infill, and you see that the phantom hole shapes are still there based on our phantom hole designs. So we still have our structural reinforcement with completely hollow shells inside. And all we did for this process was just stop the printer midstream so we could see the internal structure. So case study 2 led us to see some of the best practices. You can see some of the models we used. This was the open spline, or the freeform splines that we did to create the one design. There's the ring phantom holes that we used to create the solid core. And we just have to get our offsets right so we leave enough material to be solid in between the walls. But then on to case study 3, the one that really matters. The one that actually controls sort of like your results and the testing the data. And so this one we want to spend a lot of time not only looking at some real force loading and stress, but also what is the best way to resist that stress? What type of phantom hole designs could we utilize to make our parts better? And our process for comparison was we would take the exact external same shape, the 10 by 10 by 35, and we would set them so that they were equal mass. So for whatever mass it took of material to do the phantom hole version, we would make sure that we increased infill on the control part so that it would have the exact same version. in terms of mass. And that way we had an apples to apples comparison in terms of material utilization. So our test was set up fairly simple. We used Prusa i3 Mark II to print one part at a time. That way we got them the best possible chance of performance. We used a Mark 10S test stand, tensile tester, and we had two different loading conditions. One was a typical shear test, and the other was a typical flexural test spanning the part. So very, very straightforward process. Now when it came down to the designs of the phantom holes, we got to be creative. So for the shear test, we designed a phantom hole solution we called the shear stopper. And knowing where the shear stress was going to be was the key thing. We knew where the stress was going to occur, so we designed our phantom holes to match that shape. So you see these kind of parabolic shapes that are sort of plates that we just duplicated across the pattern of the part. Of course, again, they're holes. And so it would create a solid core of this shape right in the center of the part. For the flexural testing, we had a couple of different designs. We had one we called the pyramid steps, where you can see it reinforces the bottom flange by creating planes of phantom holes that would step themselves up, and then one plane across the top that would reinforce the top flange of the beam. Then, of course, we had what we call the C-ring, which was sort of an inverted triangle at the top flange, a little bit longer C-shape phantom hole design across the bottom flange, and you'll notice that these actually aren't complete holes, they're actually just rings, so that the phantom hole pattern comes around it. And you also notice that the C-ring design has no material back here or here. This is where the stress is, therefore the material concentration's there, and the shape of the stress is sort of mimicked. Here's a couple pictures of the fabricated parts that were stopped mid-fabrication so you can see the cross sections. This is the shear stopper. As you can see, solid core. Notice how little infill is right here or there. This is the C-ring design, and you're seeing that C shape at the bottom as it's built up. Again, noticing hardly any infill material in these areas. Its counterpart, same length and width, but it's actually full of honeycomb. So we probably ended up having 30%, 20%, something of that nature in terms of its control counterparts. The shear stopper test, or the shear test in general, you can see the data on the screen. The pH version is the phantom hole version. The control is the one that just has more infill. You notice that we had them as close as we could in simulated mass. We actually allowed the control counterpart to have a little bit higher just to give it a little cheating capability. But you can see the data. In shear failure, we actually had nearly 1,000 pounds resisted by the shear stopper before it failed. 963 on the first test, 971 on the second test, whereas its control counterpart was only able to take about 600 pounds before the failure point. For a percent difference of force, 45%, 48%. So in the shear stopper test alone, we realized we had extreme capability. Excuse me for 1 second. Thought I had canceled that off, sorry. We had extreme performance differential between the two. And overall, pretty successful in terms of simulation resulting in the product that we wanted. So we were able to focus the material where the stress was and get the results that we sort of anticipated. On the flexural testing, same kind of result. So we were able to compare the control counterparts to their phantom hole versions. The C-ring design outperformed the pyramid steps. It was a better design, so we got better results out of it. But even the pyramid steps outperform its control counterpart by 20 to 30%. So even our weaker of the design applications still outperformed in terms of material efficiency. However, the C-ring did extremely well. You can see that it hit up to an average of 46% improvement over its control counterpart that was just conventionally infilled with normal slicing settings. So we were pretty excited about the process. We were pretty excited about what the opportunities were and what we could do with this. And we're looking at numbers where we're getting 30%, 36% average between the two higher than your standard, and 46% higher in the shears. And we're very excited over the fact that the shear stopper itself could resist nearly 1,000 pounds before failure. So overall, we were pretty pleased with the technique. We thought that it had a lot of applications, and we learned a lot from the process too. So overall in the technique, there's a couple conclusions that we realized. First off, the methodology clearly allows for more efficient material usage. You basically can put material where you need it, in the shape that you need it, inside the part, and reduce the material where you don't. Obviously, this is going to potentially result in less fabrication time. So now you don't have to have an infill of 50% when your part is breaking in the middle. You can just put all that material in the middle and set your infill back down to maybe 10 or 15%. Obviously, fabrication time is a big deal in production when you want to, part after part and reduce time. Multi-material applications are possible with this. At the end of the day, we're getting better, stronger, faster parts with low-cost FDM. And like we said, that's a real passion for us. We want to see more folks getting into the business of using low cost. They don't have to go out and buy high equipment to get started. They can go out and buy low-cost equipment and start producing products right now and then scale up as they need to. We think it's an incredible business model that this technique can complement significantly. We did learn, however, there are some things you have to watch out for in the process. For one, it does help if the designer understands mechanics of materials. So for example, if we're actually designing a part where we know the load's going to be, does the designer understand how the internal stress is going to result from that load? That's a key thing because that helps you shape your phantom hole to make the internal structure that you want. Also, we've noted that there needs to be a finite element analysis component to the process. Now, the data a person might pull from the FEA won't be realistic because most FEAs are not accounting for additive manufacturing processes. However, you can use the FEA imagery to show you on the shape where the stress is going to be, and that's how you can shape your phantom hole to match that. So the data may not be perfect, but the imagery it provides gives you good design guidance. We also learned that the technique does not really work well with your low-cost SLA resin-based systems. Those systems with a laser precision, they'll generally just make the holes. Also, many of those systems just create solid structures anyway, so there's not a real infill issue. The other part of the problem is we don't really know how many combinations of CAD and slicer softwares this will work with. We used Autodesk Inventor, we used Autodesk Fusion, and we used Simplify 3D. And we've tested it out on a couple other CAD packages and a couple other slicers, but we haven't tried them all. So we don't know that it'll work with every slicer package. Some slicer packages may just see it and say, that hole's too small to worry about, and it'll just infill as normal. We've also seen some cases where you can orient your phantom hole a certain way and the slicer doesn't see it at all, and therefore it doesn't do an internal perimeter shell around that. So those are kind of things that we've learned to watch out for over time. And there's more to learn. Obviously, in the process, we're testing it more and doing more products, so we hope to have more results from it over time. Overall, though, the phantom hole technique, very, very simple. You're essentially making shapes that can't exist because they're too small. The slicer doesn't realize that, and so it gives you internal walls to match that shape and reinforce what you need. And it can be utilized by everyone. This is software and a technique more so than anything else. So it allows you to improve your process over and over and over by testing and reallocating material where you need it and from areas that you don't. So this can be a big boon for folks that are using low-cost FDM for not only prototyping, but also in-use production, tools and fixtures. It creates a tremendous amount of opportunity to develop this. So overall, some great stuff. And we do have some materials that you can check out on the next screen. So you can contact me for questions if you have any. There's my email address right at the top. Also, friend us on Facebook. We use social media a lot for job opportunities and getting stuff out there, research that's out there. And also, there's the demo that we have provided. The demo actually includes that you can use on your screen there. It will take you to a YouTube video where we've prepared about a 20-minute demonstration of the technique, going through all the steps and the processes, the logic behind it, and so you can check that out. However, you can also check it out from our own webpage. We have a lot of our research and data available on our webpage, and if you want to find it, it's pretty easy. If you'll just Google the term SCC 3D printing, it'll take you pretty close to my webpage. You scroll to the bottom, there's a blue button on the webpage that says Research and Grant Materials. Go there, and you'll see all kinds of links and videos and tutorial information over our process. So all in all, we want folks to use this, let them know how it has improved the performance of their products. We want to see it being used more in commercial applications. We want to get it out there and just see the phantom hole technique used over and over to make your stuff better. And we look forward to hearing those stories. Overall, I want to say thank you again to Tennessee Tech University for the opportunity to do this. AM Watch, this has been a great opportunity for us to get a word out. And we are excited to announce the phantom hole process has a provisional patent on it, and also will be featured in the upcoming International Journal for Rapid Manufacturing. So you can see more of the data when that rolls out. So thank you all, and happy printing.